Professor T.P. Singh, and he is a distinguished theoretical physicist renowned for his contributions to the field of quantum gravity, foundational questions in quantum mechanics, and cosmology. He served as professor at Tata Institute of Fundamental Research in Mumbai until 2022, and currently a visiting professor at IUCAA, Pune. Over nearly 4 decades of academic engagement, Professor Singh has significantly advanced our understanding of quantum measurement, gravitational collapse, and the unification of fundamental forces. His work is particularly recognized for exploring the interface between quantum theory and general relativity through novel frameworks such as stress dynamics and spontaneous localization. Processing scholarly impact is evidenced by over 130 research publications, numerous invited talks, and prestigious international conferences and repeated accolades from Gravity Research Foundation and Foundational Questions Institute. His interdisciplinary research spans octonic unification models, quantum classical dualities, and emergent space-time, earning him global recognition. He has also played a pivotal role in organizing major scientific conferences and delivering public lectures that communicate deep physics in an accessible manner. Professor Singh's efforts have made him leading figure in quest for unified theory that bridges quantum mechanics with the structure of space-time. So now I invite Professor Singh to start his talk. Yeah.
Okay, thank you, Professor Pati, for your very kind introduction. I would also like to thank the Bhaktivedanta Institute and CDAC Patna for giving me this opportunity to present this idea here. Thanks also to the organizers for their very kind hospitality. A special thanks to Debashis Khan sir for being, a single point of contact for all our queries. And my special thanks also to my young friends Nikhil and Rajesh for very kindly helping me out during this stay. So this is what I want to talk about today. The title of the talk is, do extra dimensions of time help resolve the puzzle of quantum non-locality? The puzzle is also known as the Einstein-Podolsky-Rosen paradox, as you may have heard of. So what is the quantum non-locality puzzle? It's a signature of a conflict between quantum mechanics and special relativity. It is as if there are some quantum phenomena which are happening at a speed faster than that of light, which clearly is not in agreement with special relativity. So what are we supposed to do about it? Maybe we either modify quantum mechanics, or we modify special relativity, or we modify both. The purpose of this idea is to show that you can get away without modifying quantum mechanics, without modifying special relativity, provided we are willing to consider that there are more than one dimensions of time. So we are comfortable with there being 3 dimensions of space, left and right, one dimension, front and back, another dimension, up and down, the third dimension. But we think there's only one dimension of time, past, present, and future. Time flows along a line. So if we think of there being, say, 3 dimensions of time, what does that mean? There is no up time and down time, and there is no front time and back time. There is only one kind of time. But we have to allow for the possibility that just as scientists consider additional spatial dimensions, which might be very tiny and not yet observed, there might be additional dimensions of time which are not yet observed but are very tiny but still playing an important role in solving the non-locality puzzle. Okay, so this is a report on some recent work done with my students, Mohammad Furqan, who's at IIT Delhi, Samuel Wesley, who's at Madras University. So we published this result in this paper recently, and there is also an accompanying preprint. Does our universe have more than one dimension of time? So this is the plan of the talk, which is divided into 4 parts. Firstly, how to make sense of multiple time dimensions, recalling what is the Einstein-Podolsky-Rosen paradox, also known as the quantum non-locality puzzle, and how multiple times could be a possible resolution of the EPR paradox, and that is a theoretical idea, and how can we possibly test this idea experimentally, whether or not it is correct. Okay, how to make sense of multiple time dimensions? So as I just said in the beginning, time has a past, present, and future. Let us call that absolute time, time that flows. Now, absolute time should be distinguished from what Newton called common time. Common time is what clocks measure. Common time is not the time that flows. Why is it important to make a distinction between absolute time, capital T, and common time, small t? Otherwise, we run into a paradox in defining motion and time. To define motion, we need time. If this bottle is here at instant t1 and it is here at instant t2, we say it has moved. To define motion, we need time. But how do we measure time? We measure time by the motion of the hands of a clock. So to measure time, you need motion. To measure motion, you need time. Obviously, there's a paradox. Newton was very aware of it. So he said there is an absolute time t, capital T, that flows, which is what is used to define motion. To define motion, use absolute time. And if you want to measure time, you are measuring common time. What is measured using the motion of hands of a clock is this common time, little t. You measure common time, you use absolute time, capital T, to define motion. So then there is no paradox. And then you make a grand assumption that absolute time is equal to common time as a measure. As a measure of absolute time, the common time measured by hands of clocks is good enough. But common time does not flow. This is clear for Newton. Little t does not flow. The little t is like a coordinate. Spatial coordinates do not flow. There is x, there is distance x, distance y, distance z, it does not flow. Similarly, coordinate time does not flow. It is absolute time which flows. If we are happy to make that distinction, then we can live with multiple times. So instead of one common time t, let me have, let's say, three common times. Right. So before I go to that, I'll come to this point that once you make a distinction between absolute time and common time, it does not matter whether you have one common time or three common times, we'll still have one absolute time. Absolute time will be retained despite what Einstein suggested. According to Einstein and Minkowski, coordinate time little t becomes part of space-time in special relativity, four-dimensional space-time, t, x, y, z. Einstein proposed that we abandon absolute time in special relativity and in relativity in general, although Lorentz did not agree with that. Lorentz had a Lorentz ether theory version of special relativity, which agreed with all the experimental predictions of special relativity, but retained absolute time, capital T. So is it really desirable or necessary to abandon absolute time, capital T, in relativity? Perhaps not. We can do special relativity with an absolute time, capital T also. What we have to say, the space-time evolves in absolute time, capital T. Normally we think of spatial surfaces which evolve in common time, little t, but we'll think little differently. If you have a space-time trajectory, the location of a particle on the space-time trajectory is to be marked t, x, y, z. This location is changing with absolute time, capital T. So there is it is entirely possible to do special relativity while retaining this absolute time capital T. It also helps understand cosmology better. Cosmology suggests, because of the temperature of the cosmic microwave background, which is isotropic, same in all directions, and it has a definite temperature capital T. In which frame is that temperature? If you change the frame, the temperature will not appear isotropic in all directions. So there's a special frame and an absolute time picked up by the cosmic microwave background in cosmology. That time we may identify with this absolute time capital T, which flows. And for various reasons, quantum theory becomes more manageable, more appealing, more elegant if it has an absolute time capital T. Because as you know, in quantum theory, we raise spatial coordinates to the status of operators, but we are not allowed to do that for time. We need a time parameter, a classical time, even in quantum theory, because you want to define evolution. If you had an operator time, you won't know how to define evolution. So quantum mechanics, even relativistic quantum mechanics, treats time and space differently. Spatial positions are operators, whereas time is not. But there are generalizations of quantum theory in which this coordinate time, common time t, is also made an operator, and evolution is defined with the extrinsic time, which we may identify with this absolute time capital T. So I'm saying there are advantages to retaining an absolute time even in special relativity, even in quantum theory, and treat the common time little t as a coordinate. In that case, as I said some time ago, it does not matter whether we have one common time coordinate little t or whether we have two or three. So if we retain absolute time capital T and treat coordinate time little t on the same footing as spatial coordinates, then objections against multiple coordinate times disappear. There's only one time that flows, but I have three time coordinates, just as I have three space coordinates. And let's ignore this second point, which is technical. A theory known as Alan Cohn's non-commutative geometry, along with a certain theorem, permits the origin of an absolute time which is not present in Einstein's theory of general relativity. It comes from non-commutative geometry. So let us say we are given absolute time capital T, and our work on unifying forces suggests that the universe actually is six-dimensional. It has three dimensions of space, three of time, two of which appear to be hidden or very tiny. This is also appealing. Why three space and one time? It's better, as it seems more natural. There is three space and three times. So if you are familiar with special relativity, the line element, the distance between 2 points, one is at the origin and the other is at t1, t2, t3, x1, x2, x3. The distance between those 2 points will be given by c square, where c is the speed of light, bracket, t1 square plus t2 square plus t3 square minus the spatial coordinates. So this is the Minkowski line element, but now generalized to six-dimensional space-time. There is still an absolute time capital T in which this space-time will evolve. Okay, so let us see, let us agree that we have this six-dimensional space-time. Now, a little bit of mathematics. It can be shown using a mathematical theorem that a six-dimensional space-time can be decomposed as two overlapping four-dimensional space-times, which we call M4 and M4 prime. These have relatively flipped signatures, meaning our 4D spacetime M4 has three dimensions of space and one in time. That's what we see. The other 4D spacetime M4 prime has 3 dimensions of time and 1 of space. That is what I call a flip signature. They have 1 space and 1 time in common. We are 3 plus 1, the other one is 1 plus 3, and 1 space and 1 time is common. So, the total there are 6. M4 is our familiar 4D space-time. Gravitation is the curvature of the space-time of this of the geometry of this space-time. That is Einstein's general relativity. What our work suggests that M4 prime, the second 4D space-time, also has a geometry like Einstein's geometry of our space-time, but the curvature of the second space-time is to be interpreted as the weak force. I will not go into this. You know there are 4 fundamental forces observed in nature. The strong force which binds nuclei, and gravitation and electromagnetism we are familiar with. The weak force does not bind anything. It is responsible, let's say, for interactions with neutrinos. In fact, I will not go into detail. The weak force is universal like gravity. In many ways, it resembles gravity and Einstein's general relativity. So, that is what motivated us to suggest that the weak force is the geometry of the second 4D space-time. The two 4D spacetimes arise from the 6-dimensional spacetime after a process of so-called spontaneous symmetry breaking. So, before the symmetry breaking, the spacetime was 6-dimensional. It had 3 times and 3 space. Then a symmetry breaking took place in the early universe to give rise to our 4D spacetime M4, whose curvature is gravity, and the other 4D spacetime M4 prime, whose curvature is the weak force. Now, this is the crux of the idea which will be relevant for non-locality. Quantum systems experience both the 4D spacetimes. One time and one space are overlapping. Theory tells us that the original spacetime is not 8-dimensional. That comes from theory. It is 6-dimensional. And there's a theorem that I can embed two 4D spacetimes inside 6D, provided they have opposite signatures and provided they overlap in one time and one space direction. But they will have their own metric. M4 prime has its own metric, which is very tiny. The distances are very tiny in M. The distances are of the order of the weak force. So, in M4 prime, the boundary of the universe is at 10 to the minus 16 centimeter. In M4, the boundary of the universe is at 10 to the power 28 centimeters, 10 billion light years. But how far something is depends on the metric, on the geometry. So, from the point of view of M4 prime, things are not far. They are actually very close, which is what will enter into non-locality. So, M4 and M4 prime different metrics, but they have one overlapping space, and comes out from starting from fundamental axioms of octonions and Clifford algebras. It follows from some other starting assumptions. And if it was 8-dimensional and no overlap, there will be no interaction. Particles in my universe have to feel the weak force. That is only possible if there is an overlap. Otherwise, weak force will only be felt by particles in M4 prime. M4 prime should experience general relativity. M4 should experience the weak force. The overlap enables that. So, like I said, quantum systems experience both the 4D space-time. Classical systems and detectors are only in our 4D space-time. But quantum systems are in both 4D space-time and equivalently hence they are in 6 dimensions. So, I am saying classical systems live in 4D, but quantum systems live in 6D. The two additional dimensions are like those of time, but they are very tiny. And the curvature of those two additional dimensions is given by the weak force. So, reinterpreting the weak force. Okay, so that is my introduction to multiple times what is the origin of the theory. Now let's move to the second part of the talk, the Einstein-Podolsky-Rosen paradox, and then we'll put the two together. This you have heard of yesterday. Professor Dipankar Home talked about it, Professor Leggett talked about it. So before we get into the version that EPR gave in their 1935 paper, the same difficulty of quantum non-locality can be explained in a very simple way. Suppose there is a source here which is emitting electrons one by one. An electron is emitted, it has an associated wave function which spreads spherically in all directions. Okay? The wave function of the electron is spreading. Let us imagine that at some distance away, we have a sphere of many detectors. Detector D1, D2, D3. The entire celestial sphere is filled of detectors. Now let us make those detectors very far away. For example, let us put that sphere at the end of the universe, or as far away as the Andromeda galaxy, or even farther. One day, the electron wave will arrive at that sphere of detectors, and then we know what will happen. There will be a collapse of the wave function. Only one of the detectors will click. Which one we don't know. Quantum mechanics tells us, according to the Born rule, there are probabilities for each detector clicking. When a detector clicks, before that, the wave function of the electron was everywhere in the universe. Doesn't matter how big the radius of the sphere is, it is everywhere. The moment a detector clicks, the electron is at that detector. It is no longer at any other detector. The wave function must instantly go to zero at every other detector. How does this happen? When suppose detector D1 clicks, it sends out a light beam to all the other detectors. Think of a detector D2 which is at the other end of the diameter, other end of the universe. The wave function there has to go to zero even before the light signal can arrive. The light signal may take a billion years to arrive, but the wave function cannot wait that long. It must go to zero instantly, and that is the quantum non-locality puzzle. How does, at the time of the collapse of the wave function, how is this information, this knowledge, this influence communicated instantly as if it is violating special relativity? That is the sense. And then Einstein, Podolsky, Rosen, EPR for short, made it more precise. That is what led on to Bell inequalities. So this is a formal definition of locality, as you know. If an event takes place at a point A in space at a point at a time Ta, it can influence a later event happening at B at time Tb only if the event B is on or inside the light cone of A. What does that mean? Suppose a light signal were to be sent to point B from A at the instant when A happens, then event B can be influenced by event A only if B does not take place before the light signal arrives at B. So this is understandable. This is the definition of locality. So it is assumed that for B to be influenced by A, something travels through space from A to B. This something cannot travel faster than light. That is, the laws of special relativity are obeyed. So this is locality. In the classical world, locality holds. So suppose from Earth, from A, location A, a laser beam is sent to the moon at to point B, and an explosion happens at B. Clearly, the explosion can be influenced by A only if it happened after the light beam arrived. That is locality or causality. So the classical world is local. It also obeys realism. So we classical world has local realism. So I decided to call our observers Asha and Babu instead of Alice and Bob, but you can of course understand. So what is realism? That from a space station X in the middle of A and B, Earth and Moon, two balls are sent out at this in the opposite directions. One ball has a mass of 100 gram and a diameter 10 centimeter. The other ball has a mass of 99 gram and diameter 9 centimeter. These are properties obviously which are there in the ball a priori, that is realism. These numbers are known to both Asha and Babu. And suppose Asha measurement measures 100 gram, it clearly is known to Asha immediately that the other ball is 99 grams. But that doesn't mean that Asha's measurement has influenced the other ball. Asha's measurement does not influence the other ball because these properties are given a priori. They don't depend on the measurement. So that is realism. The classical world has local realism. The quantum world does not have realism in the following sense that now if instead of those two balls, consider that a pair of electron and positron with total spin 0 is sent out from the space station. Again, one going, the electron going to the earth, the positron going to the moon. So we call this a singlet state. A singlet electron positron state is created at the space station X. The electron spin is measured at the earth. The positron spin is measured at the moon. One measurement influences the other non-locally. This is the difference from classical mechanics. So realism is not there. So let us understand how that is happening. Suppose Asha has an apparatus or two sets of apparatus, one which measures spin along the x-axis, so you could get plus x or minus x, one which measures spin along the z-axis, you can get z and or minus z. Similarly for Babu, if Asha measures spin along z and finds the result plus z, the positron spin instantaneously collapses to minus z, irrespective of what it might have been before. There is a change, that change is instantaneous. Or if Asha measures spin along x and finds the result minus x, the positron spin instantaneously collapses to plus x. One measurement influences the other non-locally. Let us make this more interesting now. Namely, so what is the EPR paradox? Let us say that after the electron positron pair has been released and is in flight, that is when Asha will decide whether to measure along x or along z. This decision is taken in flight. Now suppose, so EPR said let us assume locality. They want to assume locality, no faster than light influence. So if Asha had chosen to measure spin along z and found the result plus z, the positron spin must have been minus z. So EPR assume locality and realism. That then they show there's a contradiction with quantum theory. So if Asha chose to measure along z and found plus z, the positron would have been minus z always. And if Asha chooses to measure along plus x and find along x-axis and find minus x, the positron spin must always have been plus x. So if there is realism and the positron spin was already known a priori, then depending on what Asha measures, chooses to measure, the positron spin would have had to be along z as well as along x. That's the only way to make sense of Asha's measurements, that the positron had a definite spin along z and a definite spin along x if locality and realism are assumed. And this obviously is impossible in quantum mechanics. The electron cannot have a definite spin along x as well as along z. The two operators do not commute. So EPR concluded that if local realism holds, which they want, hence then quantum mechanics is incomplete, more information is needed. So in order to save local realism, EPR proposed that quantum mechanics would have to be modified to have additional degrees of freedom, what came to be known as local hidden variable theories. So to make quantum mechanics consistent with local realism, you have to assume additional degrees of freedom so that the positron could have had definite spins along z as well as along x. Then, as you know, famously, Bell showed that Asha and Babu can perform measurements on correlated systems like the electron-positron pair, whose statistical outcomes agree either with local hidden variable theories or with quantum mechanics, but not with both. And as you know, if it is local hidden variable theories, the correlation has to be below some bound, the Bell inequality bound. And if the correlations, if local hidden variable theories don't hold and non-locality is there and realism is violated, then the Bell's inequalities are violated. And as we know, experiments confirm quantum mechanics and non-locality and rule out local hidden variable theory. So, although EPR proposed to modify quantum mechanics to preserve local realism, Bell's inequalities and their tests through experiments show that local realism is not possible. Quantum mechanics and non-locality are confirmed. So, if there are local hidden variable theories, that is not possible. Any hidden variable theories would have to be non-local. So, quantum non-locality is definitely there in the world. There is an influence outside the light cone, as if there is a faster than light influence. Now, does this influence violate special relativity? So, we can ask a very straightforward question. Would EPR have written their paper in 1935 if they thought special relativity is not violated by quantum non-locality? So, it was clear to them that quantum non-locality violates relativity. And we can ask a hypothetical question, how might Einstein have reacted to Bell's theorem? Einstein died in 1955. Bell's theorem was proved in 1964, tested experimentally later. So, how might have Einstein reacted to the experimental confirmation of quantum non-locality? What would he say? To my thinking is Einstein would say we have to modify special relativity. The structure of space-time in quantum mechanics cannot be described by special relativity because relativity demands locality, quantum mechanics violates locality. So, the two cannot go together, and since experiments confirm quantum mechanics, relativity has to be modified in quantum theory. Yeah, so it is true that quantum non-locality cannot be used to send information faster than light. So that is called microcausality. The commutation relations in quantum theory vanish outside the light cone. Although there is a EPR paradox, there is quantum non-locality. Alice cannot use that to send a signal to Bob faster than light because the signal is that I have measured, let's say, plus z. That information can only be sent later at the speed of light. So, information does not travel faster than light in a EPR measurement. That is called microcausality. So, we say quantum theory is non-local yet microcausal. The Schrodinger evolution is microcausal, but the collapse of the wave function happens instantaneously and is non-local. So, there is this very fine balance between quantum mechanics and relativity. You cannot send signals faster than light, but there is still some influence, as if some influence travel faster than light. And what are we to do about that? Yeah, so this is just to summarize what I said. There is a non-causal influence outside the light cone, as if the quantum system is oblivious to distance. You mentioned this yesterday in your talk, Varunji mentioned. This means that the light cone is irrelevant as if for the quantum process, EPR process. Hence, we should be able to describe this process without referring to the space-time of relativity. And note that it is the collapse of the wave function, the absence of macroscopic superpositions, is what is responsible for quantum non-locality. Hence, quantum foundations are deeply connected to quantum gravity and the structure of space-time. And this slide just makes us ponder in the micro world, as Haridas sir talked, superposition holds. It has been tested for up to objects made up of 10 to the 4 nucleons, 10 to the 4 AMU atomic mass units. The micro world has superposition but and non-locality. The macro world does not appear to have superposition and it has locality. So, you go from superposition and non-locality to no superposition and locality. What is happening in between? See, where does this transition take place? This is something worth thinking about. Okay, so Einstein would agree, would say that because quantum non-locality is observed, we must modify special relativity. What we came across, and this a couple of other researchers also gave the same idea. Let's slow down. Can we preserve quantum mechanics and relativity? But who told us that the universe is four-dimensional? Let us add one or two additional dimensions of time. The sense of this little bit of mathematics, which I'll just go through, is that in the higher dimensional space-time, there is locality. Influence travel from Alice to Bob or from Asha to Babu at a finite speed, speed of light. Asha made a measurement along Z, let's say, and got plus Z. A signal traveled in the six-dimensional space-time at a finite speed, at the speed of light. But our detectors are not in 6D, our detectors are in 4D. The detectors and Alice and Bob are not aware that there are additional time-like dimensions. So, even though the influence was local in the higher dimensional space-time, it will appear to be non-local in 4D space-time if we are ignorant of the additional time-like dimensions. The additional dimensions have to be time-like, they cannot be spatial. So, here the little bit of simple math which shows why this happens. Suppose this, consider this example of a 3D space-time T2, T1, X1. It has one space and two times. Our universe is two dimensional. Just in this example, T1, X1. The bigger universe is three dimensional, T2, T1, X1. The distance between two neighboring points is dt square, dt2 square plus dt1 square minus dx1 square. Suppose the separation between Asha and Babu is ds square and it is positive. Greater than equal to 0 means it's time-like or null. The separation between them is causal. That is, any information from Alice to Bob will go at most at the speed of light. Now, consider a special situation that even when dt1 is 0, the change in the time coordinate in our space-time is 0, ds square equals then dt2 square minus dx1 square is still positive. Consider a situation like this. Now, when we project from 3D to 2D, that is from the higher dimensional space-time to our space-time, what will we do? We are not aware of dt2. We are not aware that there is additional time. We will set dt2 to 0 and conclude that ds square is just minus dx1 square, which is now negative. This is a space-like separated interval. It will appear that there is an influence outside the light cone, a non-local influence, precisely because we were not aware of the additional time-lag dimension. The event is causal in the higher dimensional space-time, but appears non-causal and non-local in the lower dimensional space-time. So, this could be a possible way to resolve the EPR paradox. The tension is removed minimally. We did not modify relativity, we did not 5 minutes, yeah, we did not modify quantum mechanics, we just added additional dimensions of time and we did not add those time dimensions to solve the EPR paradox. We came to that from a theory of unification which suggests that space-time has extra time-like dimensions. So, this picture just shows how that can happen, how our time-like interval starts to look space-like if additional time dimensions are ignored. What's very important, this we should discuss with Professor Dipankar Home. Bell inequalities will continue to hold. I have not made any changes. I have just said that there is an additional path to go from Asha to Babu. So, there are two ways to give up local realism of classical mechanics. You can give up realism, or you can give up locality, or you can give up both. What normally is suggested is that we maintain realism like in local hidden variable theories, but we give up non-locality. So, that is realism plus non-locality. But how about giving up realism and maintaining locality? That is what I suggest is happening here. We call it indeterministic locality. Instead of deterministic non-locality, like in non-local hidden variable theories, we have indeterministic locality. Non-locality is in 4D is only an illusion, it's effective. It seems to be non-local, it's actually local. So, to summarize, giving up local realism while retaining locality, only giving up realism. So, the outcomes of measurements are not predictable. They lack realism, but there is locality. So, hence, Bell's inequalities will continue to be preserved. So, this we realized, came to know after our paper that just a few months before us, Marco Pettini has given the same idea that additional times. So, this is his paper, Quantum Entanglement Without Non-Local Causation in 3 two-dimensional space. So, 3-dimensional space, 2 of time. So, he is given the same idea that if you have additional times, you can solve the EPR puzzle. This researcher also gave this idea 2017 in his theory of emergent quantum mechanics, origin of quantum non-local correlations to having extra times. This is our recent paper. Okay, so the last point is that equivalently the photon path in 6D from Asha to Babu can be thought of as a superposition of two paths, one through each of the 4D space-times. So, photon is traveling through our space-time M4, a newly predicted particle, the dark photon, is traveling through M4 prime. If the second spacetime is curved by the weak force and has a range of around 10 to the minus 16 centimeters, then path length and travel time to the second spacetime is extremely short, compact dimensions. So, in fact, what is happening is Bob is very far from Alice in our spacetime, but in the second spacetime there is another path for light, for the dark photon, where it gets to very quickly. You could call it a quantum wormhole. So, if it takes to go, let us say, 10 billion years to go from here to here in our space-time, through the other space-time it takes 10 to the power minus 26 seconds. The difference of 44 orders of magnitude. That is why it appears instantaneous. It is not instantaneous, but extremely quick. So, that is why there is an influence traveling at the speed of light through the second spacetime. It travels at the speed of light, but the distance is very short, so it gets there very quickly. So, it is in this sense that additional dimensions of time help solve the EPR paradox. This is some discussion of the possible experimental tests. I want to leave some time for discussion, so I will not go through this. This is the last slide. You heard this in Marcus Muller's talk, that what he called box world theories, our 6-dimensional space-time theory, quantum mechanics in 6D, turns out to be a box world theory in his sense. Correlation stronger than the quantum Cyrilson bound of 2 root 2 are allowed. This we show in our paper. So, if such so-called supra-quantum correlations are discovered, which are in the box world sense, if they are discovered experimentally, that would be evidence, possible evidence for 6-dimensional space-time. So, you get the gist. There is a EPR paradox which needs a solution. We have proposed a solution through additional times, basically creating a quantum wormhole which gives us very short path to travel from Alice to Bob. Now we have to see if experimentalists can test this idea. So that's all. Thank you very much for listening to me.
Thank you, Professor Singh, for very insightful and thought-provoking talks.
So thanks, TP, for a very nice talk. So just a
Sachin.
comment and a question.
Yeah.
The comment is regarding these so-called non-local realist models. In fact, as you know, Leggett's crypto non-local model was one of the major attempts in those directions. But that is not, unfortunately, verified by experiments. And so I don't know, how strong is the conclusion that indeed quantum mechanics is real but non-local. That is one thing. And the second comment is also about the absence of macroscopic superposition. Again, the GRW line of works, which you've also contributed to in a large way, have not been experimentally verified.
Yes.
So far as the experimental status today is concerned, we do not really know, whether nature or quantum mechanics obeys non-locality or realism or neither. So that is one thing.
So
Now coming back,
just a question. So what do the Bell experiments tell?
Bell experiments say that local realism is violated. Local realism is violated.
Yeah, so I'm
But
saying that.
which of these is still not?
No, I agree. So I'm proposing
Yeah.
that realism is violated, locality is preserved. Now I'm saying let us test
That's
this
a
in
proposition.
experiment.
Fine. I agree with that. But we cannot be sure that one of them is gone. So that is one thing. And the second, anyway, we can keep debating on it. But the second more interesting is, as you also proposed, let's leave some time for discussions. So I would request you to elaborate more on what are the possible experimental avenues for treating your kind of formulation. That is what is.
Okay, so one is this test of this Cyrillson bound violation. The other test is very more direct but technologically difficult. Along the other space-time, the signal comes very quickly, but still it's finite. It's not instantaneously. Before the signal comes, if Bob makes a measurement, Bell's inequalities will not be violated because the correlation has not been established. The prediction is that a very quick test by Bob will not violate Bell's inequalities, but experimentally, that's horrendous. It's a very, very small time. Yeah. There I would agree with you. I'm not an expert. I was just thinking that let's accept that non-locality is there in quantum theory. If so, it's very worrisome, and we want to make it consistent with relativity because microcausality is there. Quantum theory is consistent with relativity. So what is going on in collapse? So we want to make a very conservative solution, and I'm happy that at least 2 other researchers have said so, and I believe the solution will be shown to be correct, but let's see what.
Professor Singh, you said that when the wave function reaches the cell detector, then any of randomly detected, they detect this wavefront and brings the collapse. Now the randomness is fundamental, if I understand correctly. But is there any way to reduce this randomness so that it becomes possible to pinpoint the moment of wave function collapse?
Yeah, very good, very nice question. And if I understand you correctly, you are saying, can the randomness be replaced by a predictive theory? There are suggestions, there are underlying theories more general than quantum theory, which are deterministic, which have no randomness, but we observe those theories at a poorer resolution. Like Brownian motion appears random, whereas the actual motion of molecules is deterministic. Deterministic theories can appear to be random if not observed precisely. You get my point? Yes, so I would all like to get rid of this randomness also, but right now limited the discussion.
So question is, if we could travel through multiple dimensions, could we paradoxically arrive at a place where we already started? Or
Yeah, that's again a very good point. To travel through these extra time dimensions, you would have to be as small as 10 to the minus 16 centimeters, because those dimensions are of the range of the weak force, only curled up like 10 to the minus 16 centimeter circle. And in that sense, they are of no, they are not accessible to classical observers like us. For all practical purposes, we are experiencing only one time dimension. So there should be no causality paradox. What is happening in the quantum world? Quantum particles can feel that circle. What they are doing, I don't know. So that is for future. Thank you very
again,
much.
so